Welcome. This section is called the addition rule, but before we get there, we're going to just talk about complementary events, which we have seen a bit already, but we'll get a definition going here. So the complement of an event A consists of all outcomes in the sample space that are not in that event. And we'll be using the letter of the event A in this case with a bar over it to represent our complement. So the rule for complementary events, I am quite certain you know already. You might not be used to using notation here, but I'll show you by example that this is pretty straightforward. So among clients of a veterinary practice, 28% are cat owners. So if you were to pick a client from the practice at random, what is the probability the client is not a cat owner? So 100% would represent all the clients. So if we took away the ones that are cat owners, we'd be left with ones that are not. And that's the rule of complements. So let me just introduce our notation here. So the probability that a client is a cat owner as a percent is 28%. So the rule for complementary events says if you want to find the probability of selecting a client that is not a cat owner, the rule says take 100%, that would be all the clients, and just subtract the ones that are cat owners as a percent. So 100%, take away the 28% that are cat owners, and that leaves us with the other 72% of clients that are not. All right, but typically we will not be working in percent when we do math operations like this. So let's talk about the decimal form. So probability that an event A does not occur. So instead of 100% to represent all the clients as a decimal, that is equal to 1. So one whole group of clients. And then if I subtract the probability they're a cat owner, I'll get the ones that are not. So the probability of not an event is 1 minus the probability of that event. So let's just go through this in decimal just for practice. So in decimal, the probability of being a cat owner, 28% is 0.28. So the probability that a client is not a cat owner, it's 1 minus that value as a decimal. And that gives us our 0.72 again, or 72%. All right, and we can also work in fraction form in some situations, like the next one. So I'd like to use the next example just to illustrate or to refresh your memory on working with fractions because it will be helpful down the road. But I also have a picture here of a Venn diagram representing complements. So this one says in a certain online computer game, there are 37 players. Of these, 12 are on the A team. The game randomly chooses a player to receive a bonus, and we're going to find the probability that the player chosen is on the A team and that the player chosen is not on the A team. All right, so in my Venn diagram here, so there's the circle representing the event on the A team, and there would be 12 people, players in that circle. Let's put the 12 there. And then I know inside the rectangle would be a total of 37. We'll just call that N here, 37. So if I knew how many were on the A team, it'd be pretty easy to figure out how many aren't, because 37 people minus 12 people would be the remaining 25 people. But we're going to go ahead again and go through some notation and review fractions over here as we switch ourselves over to probability. All right, so the probability that a player selected at random is on the A team, so that would be the 12 out of the 37 players. So we'll stay in fraction. So the probability they're not on the A team is 1 minus the probability that they are. So there's our rule of complements that we're going to use almost every day as we go through our course. So let's talk fractions here. So this is 1 minus 12 over 37. And we know to subtract fractions, we need a common denominator, which in this case would be 37. So 1 is 37 over 37 minus 12 over 37. All right. And then when we're subtracting fractions with the common denominator remains, and we're able to just subtract the numerators. Now, the reason I'm showing so much work here is because eventually, as we do future problems, I don't want to have to step through each individual step along the way to get me to this point. So when I just write this final expression, I just want to read this as here's 37 over 37, that's the 1, and then taking away that 12 over 37, which was our probability of being on the A team. So just wanting to review fractions a bit. And that answer is, of course, the 25 we knew already there, 25 over 37. And I'm also going to just make a note here that if we wanted to check our work, if we took the probability of being on the A team plus the probability of not being on the A team, those two probabilities together as a percent would be 100%. And in decimal, they would have to equal 1. So we could always check if we added those fractions, we would get 37 over 37. All right, so let's head to the addition rule. And we're going to have two cases of it. The first one is when we're dealing with events that are mutually exclusive. So visually mutually exclusive will be pretty clear because we're going to have two events where there is no overlap. So two events with no shared outcomes. So that's our definition of mutually exclusive. So if they share no outcomes, it means that the probability of an outcome satisfying both conditions A and B, in other words, the intersection of the two events would have to be 0. And let's just do this by example, and we'll see our addition rule. All right, so it says in a basket of 20 pieces of fruit, there are 7 apples and 5 bananas. We'll pick a piece of fruit at random. So on my Venn diagram here, I'm going to write n equals 20. So my rectangle represents my basket of fruit. We'll let event A be, it's a fruit that's an apple, and event B, it's a banana. All right, so hopefully it's clear that these events are mutually exclusive because a piece of fruit cannot be both of those things. So you're either going to pick a fruit and get one of the apples, 7 of those, or get one of the bananas. Now I do want to finish the Venn diagram though, because there's 20 pieces of fruit. So when we find the probability of getting an apple or a banana, we'll also know what would be left over. So of course, on the Venn diagram here, 7 plus 5 are 12 pieces of fruit. So 20 minus those 12 would leave me 8 out here. We just want to switch that into a probability question. Okay, so if we want to know the probability of getting a fruit that's either an apple or a banana, when events are mutually exclusive, all we have to do are add the individual probabilities together. And this is the same as saying union, so the combining of the groups. So we would say, let's take the probability it's an apple plus the probability that it is a banana. Okay, so I know both of those probabilities are going to have a denominator of 20. So rather than write the two fractions separately, since I know they have that common denominator, I can just now do the 7 over 20. That's my probability of getting an apple, plus 5 over 20, probability of getting a banana. So there is a 12 and 20 chance that you'll either pick a fruit that is an apple or a banana. Okay, so the probability you get one that's not an apple or a banana would be the other 8. And then just to end this, so intersection. So again, what's the probability of selecting a fruit that is both an apple and a banana? So always just a good reminder to remember that and means a fruit, an outcome that satisfies both conditions. All right, so that of course is 0. You can't get a fruit that is both, making these events mutually exclusive. All right, then we'll move on to the addition rule next when events do share outcomes, so events that are not mutually exclusive.